Okay, in the last lecture, we have seen the matrices, their characteristic equations, their eigenvalues, and their eigenvectors. So now we know how to calculate the eigenvalues, how to calculate the eigenvectors. Okay, so we'll try to move one step ahead. Now, in this lecture, we'll try to understand what is the Cayley-Hamilton theorem. Okay, so we'll think of the Cayley-Hamilton theorem now. Then, how this Cayley-Hamilton theorem helps us to understand or to miniaturize the system. Okay, so I hope all of you are able to see this Jamboard now. Are you able to see this Jamboard? Yes. Okay. Okay, so we'll try to understand what is Cayley-Hamilton theorem. Okay, so this theorem is very useful in understanding the miniaturization of the system, and then how this theorem helps us to miniaturize the system. Okay, so matrix can be used as the filter, and then using this filter several times in several combinations in linear as well as non-linear, and then it helps us to get the signal or filtered output. So if your output having some contaminations or it is having some noise, and you use matrices as a filter, and then you get an output which is clean, free from noise. Okay, so how to miniaturize this system? So this is input, then this is the matrix system, okay, or this is a filter, and then you get an clean output. Okay, so our target is to miniaturize this matrix system or this filter. Okay, so how to do it and how this Cayley-Hamilton theorem helps us to do it. Okay, so here we'll try to understand what is the Cayley-Hamilton theorem first. Okay, so let us try to understand the Cayley-Hamilton theorem. Okay, so this theorem says for every square matrix, satisfies its own characteristic equation. Okay, this is the statement of the Cayley-Hamilton theorem. It looks very easy. So it is very easy. Every square matrix satisfies its own characteristic equation. So if I have matrix A, then what is the characteristic equation of matrix A? It is determinant of A minus lambda I is equal to 0. Okay, this is the characteristic equation. So what this theorem says? This theorem says that determinant of A minus A into I is equal to 0. See, this lambda is changed by A. So this is the characteristic equation which eigenvalue satisfies, and now this theorem says that it is also satisfied by the matrix. So we can have A minus this I into A is what you'll be having. Again you have A. Okay, so you'll be having this A, and A minus A is equal to 0. So this is going to be 0 is equal to 0, which shows that the matrix, every square matrix, satisfies its own characteristic equation. Okay, so that is the theorem we have. Okay, the proof looks to be very simple. Okay, but the application of this theorem are very good number. Okay, and you can have many applications of this theorem. So one of them is miniaturization that we'll study here. Okay, so how it miniaturize the system. So the first thing that we need to understand is how to verify this theorem, whether this is true or false. Okay, so we'll try to verify this theorem. Okay, so let us try to see that the square matrix satisfies this theorem. So we'll go for an example. Verify Cayley-Hamilton theorem for A is equal to. Okay, so we have the matrix three, 1, minus 1, 2, 2, minus 1, and 2, 2, 0. So this is the matrix we have, and then we have to verify the Cayley-Hamilton theorem. That means we have to show that this matrix satisfies the Cayley-Hamilton theorem. Okay, so we go with the solution. Okay, so what we have to do is, if I want to show that this matrix satisfies its own characteristic equation, so first I should know what is the characteristic equation of this matrix. So we have, let A is equal to, so what is the matrix we have? 3, 1, minus 1, 2, 2, minus 1, 2, 2, 0. Okay, B, the given matrix. Okay, so that's going to be the given matrix. Now consider, so what we have, consider determinant of A. Okay, so what we have, the determinant of A, 3, 1, minus 1, 2, 2, minus 1, and then this is 2, 2, 0.
Sir, please send the link for the Jamboard again.
Okay, you are not able to join the Jamboard?
Yes, sir.
Okay. Yeah, I have sent it again. Okay.
Thank you, sir.
Welcome. Okay, so now consider determinant value. So give me what is the determinant value. I hope your calculators and you are calculating with me. Okay, so we have characteristic equation as, what is that? A minus lambda I equal to 0. So determinant of A minus lambda I equal to 0. Now I have this determinant. So 3 minus lambda, 1 minus 1, then 2, 2 minus lambda, minus 1, and then this is 2, 2. This will be minus lambda, and this equal to 0. Okay, so what is the value of determinant? Adesh?
4.
Is that 4?
Yes, sir.
All of you are getting 4?
Yes, sir. 6 minus 2, 4.
Okay, so all of you are getting this is going to be 4. So this is going to be 4. Now see, what is the shortcut? We know how to find out this characteristic equation for 3 by 3 matrix. So lambda cube minus S1 lambda square plus S2 lambda and minus determinant of A equal to 0. Okay, so this is the shortcut that we know. Okay, so let's have it. What you are having here, lambda cube minus, okay, what you will be having, sum of the diagonal elements. So it is 3 plus 2 plus 0 lambda square. Then you will be having plus sum of the minors. Okay, so for this 3, what will be the value of the minor? This is the minor now. So it is 0. minus minus plus 2. So this is 0 plus 2 plus what will be having for this 2 now. So it will be 0 and again plus 2. So it is 0 plus 2 plus what will be the minor for this 0. So it will be 6 minus 2 and this is lambda minus 4 and this is equal to 0. Are you getting this equation? Chirag?
Yes, sir.
You are getting this equation?
Yes, sir.
Okay. So we get here lambda cube minus 5 lambda square. What you will be having here? This is 2 plus 4 and this 4 is going to be plus 8 times lambda and you will be having minus 4 is equal to 0. Okay, so now we want to find out the factorization. So we have the sum of the eigenvalues is 5 and the product is 4. So can you guess the eigenvalues? What we know is sum is equal to 5 and we have product is equal to 4. So can you have the factorization of this 4 such that the sum is going to be 5?
2 into 2 into 1.
So 2 into 2 into 1. Okay. And this will be 2 plus 1. Yes. So it can be. So let us apply here and find out the factors. So do you get the factorization? What are the factors you have? Lambda minus 1 we have and here lambda minus 2 bracket square is equal to 0. So we get here factors or the roots as 1, 2, 2. All of you are getting this one? Are you getting this one? Minal?
Yes, sir. 1, 2.
Yes, sir.
Okay. So that's what you'll be having. Now I'll take this as equation 1. Okay. So what we have characteristic equation of A as, so what is the characteristic equation we have? Lambda cube minus 5 lambda square plus 8 lambda minus 4 is equal to 0. This is equation 1. Okay, now what the Cayley-Hamilton theorem says, see, every square matrix satisfies its own characteristic equation. So what we have to do is, we know now the characteristic equation, so we have to replace this lambda by A. Okay, so what we have to do is, we have to replace this lambda by A and we have to see that this equation comes to be 0. So when we convert this into matrix, so it will look like this. Okay, so it will be A cube minus 5A square plus 8A minus 4I and we have to prove that it comes to be 0. Okay, so when we write in terms of the real or the real field, then is 4 into 1 is there. So 1 is the identity in real field. In matrix field, the identity is I. So we have to write 4I when we write this equation into the matrix form. Okay, so this is the matrix form. In matrix form, we cannot just write 4. We have to write 4I, where I is the identity of order of A. Okay, so this is what we want to prove. Okay, now if I want to prove this one, then I should know what is A square, what is A cube. That's why we have to calculate first what is A square. So we can have A square is equal to A into A. So let us calculate this A square. So what we have, the matrix 3, 1, minus 1. So 3, 1, minus 1, 2, 2, minus 1, and 2, 2, 0 into. We have another matrix which is same. So 3, 1, minus 1, 2, 2, minus 1, and 2, 2, 0. So can anyone of you give me this matrix? Anam Sharif.
Yes, sir.
So please tell me what is A square.
Sir, row into column. 3 into 3.
That's okay. Row into column. I want you to calculate and give me this answer.
Sir, the final answer.
Yes, I want the square. What is a square?
Okay, sir.
Use your calculator and then give me the answer. Is anyone ready with the answer? If you are ready, then you can unmute yourself and then give me the answer. Others can verify that. So is anyone ready? Are you calculating with me? Please check this answer.
4.
Next is going to be 4.
4. Yes.
Next,
-4.
-4.
10.
10.
6.
6.
-4.
-4. Okay. So others, please verify this answer. Okay.
Yes, sir.
All of you are getting the same?
Yes, sir.
Okay. So now we have, so we want a square, we want a cube also. So a cube is equal to a square into a. And that's what we got the square here. So 9, 3 minus 4, 8, 4 minus 4, 10, 6 minus 4. And here we'll be having this 3, 1 minus 1, 2, 2 minus 1, and 2, 2, 0. So please calculate this and then give me the answer. Atharva,
Yes, sir.
yeah, have you calculated this a cube?
No, sir.
Yep.
I'm having a
So 25, 7 minus 12.
Row wise,
Yes, sir.
25, 7 minus 12.
Minus 12.
Okay.
34, 8 minus 12.
24, 8 minus 12.
34, 14 minus 16.
34,
14 minus 16.
14 minus 16.
16.
Okay, so you please check this. Okay. All of you, if you agree with this, then we'll go for the next step. All of you got this one?
Yes, sir.
Okay. So that's good. You got this one?
सर
Yeah.
ये 9, 9, 8, 10 है कि 11, 10, 10 आएगा वहाँ पे
Please
a
check
square
carefully.
a square
Yeah, check
9,
carefully.
8, 9, 8, 10 के जगह 11, 10, 10 आएगा ना
Okay, this will
Nine,
be
sir,
3 3s are
nine.
9,
ये
8,
same है
10.
सर, सही है.
Yes, 3 3s are 9. Then this will be plus 2 and this will be minus 2. So it will
वही
be
रहेगा
9.
सर.
Yes, this is correct. Okay.
It will not change, sir. It's right.
Yeah. Okay.
okay
So
sir my
if-
bad
yeah. So this is correct. Then this is correct. So now we got a square, we got a cube. Now we have to consider. So we have what we want to calculate a cube minus 5a square plus 8a minus 4i. This is the polynomial that we have to calculate and we have to show that this is going to be 0. Okay, so we have to show that this is equal to 0. We cannot write this is equal to 0. We have to prove it. Okay, so we have a cube. Okay, so a cube we have calculated here 25 7 minus 12. Okay, 25 7 minus 12. Then this is 24 8 minus 12. Okay, then we have 34 14 and minus 16. So 34 14 and minus 16. Now we have minus 5 times a square. So
45,
that is
15 minus 20.
yeah. Just wait. So this is 346, 346, and we have all minus 4 here. So minus 4, and minus 4, and then plus 8 times. So it is 3 1 minus 1, 2 2 minus 1,
2 minus 1, 2 to 0.
2 0. Yes. And then minus 4 times I. So it is 1 0 0 0 1 0 0 0 1. Okay, that's what we have here. Okay, so this is the polynomial that this is the polynomial in matrices that we have to simplify. Okay, so let us simplify this. So calculate 25 minus 45 plus 24 minus 4. How much we have? How much we have this one?
0.
0. Yes.
0.
Calculate the next number. So 7 minus 15 plus 8 plus 0. How
0.
much you have? 0. Okay, then minus 12 plus 20 minus 8. How much you have?
0.
0. So you please calculate all the entries and tell me what these entries are.
0.
This is 0. What about this entry?
Final answer 0, right, sir?
Have you calculated final answer?
Yeah, sir.
If you have calculated, then only tell me. Okay, so others will verify that. So if anybody has the final answer, then you please verify. This is going to be the 0 matrix. So what we got here, we got a cube minus 5a square plus 8a minus 4i equal to 0. Okay, so we can say what happened here, this matrix, okay, satisfied its characteristic equation. So this is the characteristic equation, and this is the matrix equation that we have proved. Okay, so right hand side is 0 here, and here also the right hand side is 0. So this characteristic is in real field, and we proved that the same happens in the matrix field also. Okay, so that's why we can say hence Cayley-Hamilton theorem is verified. Okay, so this Cayley-Hamilton theorem is verified. Okay, so this way we are able to verify the Cayley-Hamilton theorem. So to verify the Cayley-Hamilton theorem, what we have to do is, first we have to consider the matrix, then we have to calculate its characteristic equation. So once you know the characteristic equation of this this matrix, then we have to think of Cayley-Hamilton theorem. So after calculating the characteristic equation, what we have to do is, we have to think of, instead of this lambda, we have to think of a. So here it is lambda cube, so we need to calculate what is a cube. Here we have lambda square, so we need to calculate a square, and then put this or replace this lambda by a. So whatever the polynomial we have on the left hand side, see that on right hand side we get 0. Okay, so if we are able to get 0, then only we say it is true. Okay, if we are not able to get 0, then we say that it is not going to be satisfied. So here we have to be careful. Okay, we just consider this left hand side. We do not write equal to 0 at the beginning only. We have to prove that it is equal to 0. So we showed that this calculation comes to be 0, or this polynomial matrix comes to be 0. This is a 0 matrix, and hence we can say that this polynomial equal to 0. So it becomes the equation which is exactly the characteristic equation satisfied by A, and that's what the Cayley-Hamilton theorem is. So this Cayley-Hamilton theorem says that every square matrix satisfies its own characteristic equation. Okay, and here we proved that this matrix A satisfies the Cayley-Hamilton theorem. Okay, so is there any doubt in this example?
No, sir.
No, sir.
All of you got this idea?
Yes.
Yes,
Yes.
sir.
Yes,
Okay.
sir.
You got this idea of Cayley-Hamilton theorem, right?
Yeah, sir.
Okay. So let us try the another example. Okay. So we'll have another matrix. Okay. So we go for the next example. So I write here next example. Verify Cayley-Hamilton theorem for so I hope you are able to see this matrix. Is that visible? Is the matrix visible to you?
Yes, sir.
Minal, is that visible?
Yes, sir. It's visible.
Okay, that's good. Okay, so now we have this matrix, and then we want to verify the Cayley-Hamilton theorem. So what are the important steps? First, we need to find out the determinant. Second, we have to find out the characteristic
A square.
equation. Okay. Third, we have to find out a square and a cube if required. And fourth, we have to find out the polynomial equal to 0. So these are the steps that we need to understand or we need to follow. Okay. So what we'll be having, let A is equal to. So first, always start your answer with what is given thing. So 8 minus 6, 2. Minus 6, 7, minus 4, 2 minus 4, 3. Okay. Be the given matrix. Okay. So what we have to do next? Consider determinant of A. Okay. So what is the determinant of A? 8 minus 6, 2, minus 6, 7, minus 4, 2 minus 4, 3. So please calculate the determinant. Okay, so we have characteristic
0,
equation
sir.
of A equal to what you are getting?
0.
0. Are you sure?
Yes, sir.
Yes, sir.
Okay. Okay. So you are getting determinant equal to 0. So that makes our work more easy because determinant value is going to be 0. Okay. So what we'll be having, we want to calculate the characteristic equation now. So we have determinant of 8 minus lambda. Then what we'll be having, minus 6, 2. Then minus 6, 7 minus lambda. And this is minus 4. 2 minus 4, and 3 minus lambda. So it is going to be 0. Okay. So we have here lambda cube minus what will be having here 18 lambda square and plus. What are the minus we have here? So the minor for this 8. Okay. So what will be having here? So this is going to be 21 minus 16. Okay, plus what is the minor for this 7? So it is 24 minus 4 plus what is the minor for this 3? You will be having 56 minus 36, and this is going to be lambda is equal to 0 because we have determined equal to 0. So this determined is going to be 0, so we don't need any term minus this one. So what is the formula? The formula is lambda cube minus S1 lambda square plus S2 lambda minus determinant of A is equal to 0. So we have determinant of A is equal to 0 already. So this is the polynomial that we'll have. So we got the equation now. So can you tell me what is this equation? So what we'll get here? Lambda cube minus 18 lambda square. What this value is going to be? What this value is plus minus? Plus minus 45.
Plus 45.
Is it plus 45?
45 plus 45.
So 45 lambda. This is going to be equation 1, which is characteristic equation. Equation of A. So we are interested in characteristic equation of A. So we got the characteristic equation of A. So here one thing you need to understand, while solving the problems of Cayley-Hamilton theorem, we don't need to calculate eigen values. Okay, so we are just interested in the characteristic equation, and that we have got here. So we can get the idea that we want to calculate A cube, and we have to calculate A square. So let us consider A square. So what you will be having? A into A. Okay, so we got here, this is 8 minus 6 2, and this minus 6 7 minus 4, and this is 2 minus 4 3. Okay,
So every time we use calculator, right?
yeah, you can use calculator for this, but we have to write how do we get A square, no?
Yeah, sir.
Okay, so you can use calculator, but we need to write how do we get it. Okay, so minus 6 2, then minus 6 7 and minus 4, then 2 minus 4 and 3. Okay, so what is the value you are getting here? You can use calculator and then give this value.
$104 minus 98 46.
104 minus 98
46
46
minus 98
minus 98
101
101
minus 52
minus 50
52 minus 52
minus 52. Okay,
46 minus 52 29
that's right. 46 minus 52
minus 50 29.
and this is 29.
Yes, sir.
Okay, so we got here 104 minus 98, and this is 46 minus 98 101. Okay, and this is minus 52. This is going to be
46 minus 52
minus 52 and
29.
So this is minus 6 7 minus 4 2 minus 4 and 3. And now Give me this
1512.
1512
1 minus 1494.
minus 1494
738.
738. Next row
Minus 1494.
minus 1494
1503.
1503
Minus 756.
minus 756.
738.
738 minus
756.
756 and this term
387.
3827.
No, only 387.
Only 380.
387.
387. Okay.
Yes.
Okay. So we got here a cube. We got here a square. Okay, and a already we know. So we can try for this polynomial. Okay. So let us have this polynomial. What we can have is, consider a cube minus 18a square and plus 45a. Okay, so this we want to show that it is going to be 0. Okay, but we cannot just write is equal to 0. We have to show that it is equal to 0. So we have a cube. Okay, so we can have 1512. Okay, so 1512. Then what is the next entry? It is minus 1494. Minus 1494. Okay, minus
738.
1494. This is 738.
15.
This is what will be having
B22. 1503.
1503
B23 minus 756.
minus 756 minus
Minus 756.
756 and this is
387.
387 minus 18 times square now. So we have 104 minus 98. What is this next value? 46. So it is 46. What you can have? 101. 101, 52. This is 52 and this will be 29 plus 45 times. Is going to be A. So what is A? 8 minus 6, 2. 8 minus 6, 2. Minus 6, 2. So it is 7 minus 4. 7 minus 4. And this is 3. Is that okay? All the matrices are correct now? Now
Yes, sir.
calculate this value.
Zero, sir.
Are you sure? Meenal, what is your
Yes, sir.
value?
Yes, sir.
Sir, I'm calculating.
Calculating. Okay, Anushree,
Yes, sir.
what is your value?
0, sir.
Okay. So others, please verify this, that whether it is going to be 0 or not. Okay, so we got here a cube minus 18a square plus 45a is equal to 0. Okay, so we can say hence Cayley-Hamilton theorem is verified. Okay, so here we can see this was a given matrix. So we just have to find out first what is the characteristic equation. So if I want to find out the characteristic equation, first I need to know what is the determinant. So first we have to find out the determinant. After finding the determinant of this matrix, we got the characteristic equation. So the characteristic equation is A minus lambda is equal to 0. And now after that we write this matrix, this determinant. Then how to solve this determinant, or what is the shortcut to get the characteristic equation? So we have lambda cube minus s1 times lambda square plus s2 times lambda minus determinant of A is equal to 0. What this s1 and s2 is? So we can have s1 is equal to sum of diagonal elements. Can anyone of you tell me what is S2? What is the value of S2? How do we calculate S2?
Sum of minus
It is sum of,
diagonal element.
yes, minus of diagonal elements. Okay, so and determinant of A already we have calculated. Okay, so we know determinant of A. So determinant of A in this case is going to be 0. Then we calculate S1. So S1 is sum of the diagonal elements. So that is this 8, 7 and 3. So this is going to be 10 and this is 8, 18, and now minus. So for this 8 we have this minor, for this 7 we have this minor, and for this 3 we have this minor. So once you calculate the minors, we have to consider the sum and minus determinant. So in this case the determinant is going to be 0, so we don't have to worry about it. Okay, now once you calculate this, so we get the characteristic equation of this matrix. Okay, so once you get the characteristic equation of this matrix, let it equation 1, because later on we are going to use it. So here you write it that it is the characteristic equation of A. And what this theorem says? So this theorem says that every square matrix satisfies its own characteristic equation. Okay, so first target is to find out the characteristic equation. Okay, and once you know it, then we need to show that it is satisfied by the matrix. Okay, so here we calculated the characteristic equation. Okay, so from this characteristic equation, what we have to do is we just have to write, instead of lambda we write a cube. Then instead of this lambda, we write a square. And so we need to calculate a square and a cube. And that's why first we calculate a square. So how do we calculate a square? A square is a into a. And that's why we write it here. Okay, then what we do, we consider the row of the first and the column of the next matrix. So using this row and this column, this row and this column, this row and this column. So we got the value of a square. And once you know what is a square, then we calculate the value of a cube. So here we calculated the value of a cube. So a square into a, and then we got the value of a cube. And now we have to consider this polynomial. Okay, do not write equal to 0. We have to show that it is equal to 0. Okay, so if we consider the polynomial and then we want to show that it is equal to 0. So we consider the polynomial in terms of a. Okay, and once you consider this in terms of a, we write down what is a cube, we write down a square, and we write down a. And then after having this polynomial, we got it is equal to 0. Okay, so this zeros represent the elements, this 0 represent the matrix. Okay, and hence this polynomial equal to 0 matrix. Okay, so what we proved that this equation is exactly same as the characteristic equation that we have considered here. Okay, and hence we can say that the matrix A satisfies its own characteristic equation. So if the matrix A satisfies its own characteristic equation, that means it satisfies the Cayley-Hamilton theorem, and so here we can say the Cayley-Hamilton theorem is satisfied. Okay, or we can say we have verified the Cayley-Hamilton theorem. Okay, so is there any doubt in this topic? Is there any doubt?
No, sir.
Okay.
No, sir.
All of you got the idea of Cayley-Hamilton theorem?
Yes, sir.
Okay. So this way, the Cayley-Hamilton theorem says that the matrix always satisfies its own characteristic equation. Very simple statement. Okay. So what we have to do is we have to show that whatever the characteristic equation we calculate, if we replace that lambda by the matrix A, then the right hand side will be 0. Okay, because for our characteristic equation we always have a right hand side equal to 0, no? That's why, so we have to show that this happens in case of matrix also, and that is the theorem we have. Okay, so here with the help of these 3 examples, we have proved that the Cayley-Hamilton theorem is verified. Okay, so the Cayley-Hamilton theorem is verified. What is the physical significance of this? What is the application of this? So actually, Cayley-Hamilton theorem says that how many times and in what combination if you use the filter, it will nullify the effect. Okay, so what is the physical meaning or the physical significance of this statement, or what it means in real life? Okay, so it means that if you have a filter, a matrix, okay, then what combination of this filter or what combination of this matrix will nullify its effect. So that is the meaning, real life meaning of the Cayley-Hamilton theorem. Okay, we'll see how it helps in miniaturizing. So miniaturizing means what? Wherever the effect is getting nullified, we remove that term. Okay, so effect is getting nullified, that means we don't need that term there. Okay, so we have to find out all such portions where the effect is nullified, and that's why the system will be miniaturized. Okay, and that's why this Cayley-Hamilton theorem helps us to build the miniature of the system. Okay, so when we do the experiment, okay, we get a very large system. Okay, but if we use Cayley-Hamilton theorem to that system, okay, we are able to miniaturize the system. And this is how the Cayley-Hamilton theorem is very useful. Okay, so this matrix may be a data, maybe a filter, or maybe another system. Okay, so is there any doubt now?
No, sir.
No. Okay, good.